Hallo zusammen, ich bin der Thomas, and I will switch to English in a couple of seconds, but I do appreciate if I can speak Swiss German, it's not that often. Es freut mich mega, da bei euch zu sein, da zu reden. Ich bin immer mega gerne auf dem Gurten. Heute rede ich über Cilium und eBPF, aber auch über Isovalent. Firma mit Schweizer Wurzeln, und anstatt dass ich nur über den technischen Aspekt rede, was ich auch machen würde, möchte ich auch einen kleinen Einblick geben in unsere Wurzeln und wie die Technologie in der Schweiz entstanden ist. But now we'll switch to English, because I think not everybody in the room actually understands Swiss German. So today I will talk about Cilium and eBPF, but also about Isovalent, the company created by the founders of Cilium, which has Swiss roots. And I will share some of the early stories and how Cilium, the idea of Cilium, sparked in the Swiss mountains. And that's real. I have pictures to prove it. Who has heard about Cilium before? Who knows more or less what Cilium is about? Oh, wow, many hands. Great. Cilium, networking, security, observability, fresh in the latest release, also service mesh and ingress. We see like a big wall of Cilium users, of course many enterprises, including some Swiss logos if you look closely, as well as a variety of different managed Kubernetes platforms, including EKS Anywhere, Anthos, GKE, DigitalOcean, and so on. Cilium is a CNCF, a Cloud Native Computing Foundation project. We're currently at incubation level, and we're looking to graduate next year. As underlying technology, where all the magic happens, we're using eBPF as well as Envoy for the layer 7 processing, and we'll get into the nitty-gritty details as we dive in. Originally, Cilium was created by Isovalent. Actually, not like 100% accurate, because we really created Cilium first, and then 1 year after we have created Cilium, we created the company. But in the end, like the founding team of Isovalent also created Cilium. Today, of course, Isovalent is no longer the only contributor to Cilium. We're still at about 65 to 70% of the contributions, but that percentage is going down. eBPF. So same question again. Many hands around Cilium. Who has heard about eBPF? That's actually surprising. eBPF is this super low-level technology, right? It's been invented, it's been created for kernel developers. My background is Linux kernel development. I was at Red Hat for almost 10 years as part of the kernel team, and eBPF was a big deal in the final years. eBPF was essentially created to make kernel development easier, because guess what is the average time of a kernel change until it makes it into the hands of end users? So the time from I'm doing a kernel change and I'm sending it to Linus Torvalds, and then how long does it take for that change to make it into the hands of a customer or an end user? It's 5 years. That's insane, right? That was actually the reality before eBPF. We had to pretty much guess what would users need and want in 5 years. That doesn't sound so bad until you try to create a platform like OpenShift. I still remember early days of OpenShift. We tried to change kernel source code functionality for OpenShift, and then realized it doesn't actually make any sense, because it would take years for customers to actually be able to run such kernel versions. eBPF changes this fundamentally, because eBPF is very similar to JavaScript. So what JavaScript is to the browser, eBPF is to the Linux operating system. It allows us to extend the ability of what the Linux kernel can do. We can load programs. We can load them at runtime, similar to what the Linux kernel module can do, which was invented or intended for drivers or device drivers. eBPF is implemented in a sandbox concept, so we can do it securely and safely and still efficiently. This allows us to, instead of doing kernel source code changes, we can write eBPF programs and run them, as in this example, if a system call gets invoked. And for those without a systems background, anytime a process, an application, tries to do something with the operating system, for example, execute a new process, or fork the process, or read a file, or open a file, or send something on the network, it has to perform system calls. And eBPF programs we can run when such a system call is being invoked. We can also run them when a network packet is being received and transmitted, which some of you will probably already connect the dots. That's how Cilium performs and uses eBPF to do networking. When we do this at system call level, we can do things like filtering and observability. This is where the security aspect comes into place. And this changed two things. First of all, the time from changing kernel functionality to getting that into the hands of users went from 5 years to days. And it unlocked a massive amount of innovation, very similar to what happened to the browser world as well. And many of us can still think back many years back when we had to install a certain version of the web browser to view certain websites. You had to upgrade Netscape Navigator or Internet Explorer, whatever browser you were using. That's no longer the case because the majority of the functionality is implemented in JavaScript or a similar sandbox concept, and it's no longer extending the concept of HTML. eBPF is the same, not from a performance perspective as JavaScript, but from a conceptual perspective, and it has unlocked similar wave of innovation. Cilium is one such example. There are many more other projects in the cloud-native space, but also outside that leverage eBPF. If eBPF is this powerful, then what is Cilium about? eBPF itself is so low level, it's essentially an assembly-like bytecode language. You typically need a kernel team to use it, which is why companies like Facebook and Google and Netflix were successful using it back in 2014 when it started. It is not meant for end users. What Cilium essentially provides, very similar to what Kubernetes does for namespaces and containers, it makes it approachable for the wider set of end users. So you can utilize the power of eBPF without actually requiring to understand it. Cilium today is actually a set of different projects. Most of you probably have heard about Cilium in the context of the CNI, the Container Networking Interface, the networking layer of Kubernetes, where Cilium is a highly scalable, highly secure, high-performance CNI plugin. We'll dive into the details of all the little things it can do. We have since added several other pieces, such as the Cilium Service Mesh. We'll dive into that with a sidecar-free data path implementation, as well as Hubble, our observability layer on the networking side, and with open source Tetragon earlier this year, our runtime observability and enforcement. So this is the whole family of Cilium projects, all governed by the Cilium project. What unifies all of them is they're all using eBPF as the underlying technology to drive it. Sounds great. Cilium today is used by massive platforms like GKE, Anthos, EKSA, but where did it start? And how did that develop? Why did the idea spark? This is how we started. This is the initial Cilium Design Summit in 2016 in Engiadina, Diavolezza. It was a foggy day. We didn't see anything. It was actually the moment we realized that observability is going to be key. So that was our first design decision, that if we design Cilium, observability is really important because we could barely see more than 5 meters. Where we are today, that's Isovalent earlier this year. So we've grown significantly since back in 2016. This is when we first talked about Cilium. It's actually very interesting. It was at the Open Source Summit. KubeCon did not exist back then, or I think maybe it have been the first year of KubeCon in London. It was actually IPv6 only. We were extremely narrowed down on a next generation networking platform. IPv6 only, no concepts of network. Our vision was this is going to be the first network plugin where end users do not have to understand any part of networking. Policy decoupled from addressing, something that we take for granted today with Kubernetes, was back then a very new concept. And the giant flat L3, every application developer assumes this today. That was, or Cilium had this initial design implemented as well. And I've also included 2 architecture diagrams when we initially designed Cilium. These core elements are still the same today. So the Cilium agent running in user space, and then the kernel component running on the operating system level, utilizing eBPF, as well as the basic concept of eBPF that's used by all eBPF projects. You have source code, eBPF source code, typically in pseudo C code, and a compiler, for example, LLVM or Clang, compiling that into eBPF bytecode that then gets loaded into the kernel layer, and you can attach it to hook points, such as when a network packet is being processed or when a system call is being invoked. Whether you use Falco, Cilium, Tracy or other eBPF projects, they all more or less do the same. Sometimes this initial compilation step is already done at build time and is not performed as part of the agent. Sometimes that's still being done on every individual node or the machine that it runs on. Interesting. When did things start changing? The first big moment was DockerCon 2017. Who was at DockerCon back in 2017? Yes, I see Tim back there. To me, this was like one of the most exciting conferences, and it was clearly like a big game changer for Cilium. We had a conference talk that went really well. We had a Star Wars demo that I still have customers that talk about this demo today, 5 years later. This is when the wider community outside of network started to notice Cilium and that Cilium could actually change how we do networking, how we do security, and so on. 2017 is also when we got our first office. So you see one of our team members here ironing. This was actually, I think, the back wall of one of our conference booths, as well as the initial Cilium logo design that we have drawn on paper. 2018, we started to grow. You see the conference booth is already a bit more professional, and we celebrated like Cilium's 20. Obviously, we're engineers, so we didn't celebrate 2,000 stars. We celebrated 2,048 stars, of course, as well as actually introduced Fondue in our Palo Alto office. So this is in a random Airbnb in Palo Alto, bringing some of the Swiss culture. We also had a team building experience. We still talk about this today in the company. The snow chain incident on the Julier Pass. Some poor souls really wanted to be the first on the skiing slope, so left really early in the morning, hit the snow on the Julier Pass. In the end, they were not the first to hit the slopes. And to date, we're still using this as part of the company onboarding story. Swiss culture, I talked about this. Actually, a big part of the company. Obviously, skiing, mountains, sports. We still do a Swiss all hands every year in the company, and I think it's one of our top selling points when we hire. You get to visit Switzerland and you get to ski. It's a big part of the culture and has allowed to not only bring, let's say, the high-tech Silicon Valley structure and culture, but combine that with like some of the Swiss values, including skiing, snow, and meeting in Switzerland. In 2021 is where things started to get a bit crazy from a business perspective. First of all, we joined the CNCF as an incubation level project. And both AWS and Google started to pick Cilium for their managed Kubernetes platforms for their on-prem offerings, so for Anthos and EKS Anywhere. We had already several other smaller cloud providers like DigitalOcean as well as Alibaba use Cilium before that, but these were the first major cloud providers that started to use Cilium on a significant basis, and that was clearly a signal something is going on, that the industry is starting to standardize around Cilium. In 2022, it got even crazier. So earlier this year, we closed our Series B funding round, and you even see Microsoft on here as well as Grafana. So there are more better integrations coming along the way. We are super excited about what is happening around Cilium in terms of integrations and how it becomes the cloud-native standard around networking. So let's dive a little bit into that background of the company, how it started. Literally started in Switzerland, in particular on the engineering side. Since we have grown a lot, we're obviously a global company. We still have about 30% of our employees in Switzerland, though, so the culture and the origins will remain the same. I'm now going to dive a little bit into each individual aspect, from the CNI, the networking side, as well into service mesh and security. CNI, maybe the most boring aspect, but I think networking is never boring, even though I've been doing it for 25 years, I think. Networking is kind of never irrelevant. I'm not sure why, but we keep kind of reinventing or resolving the same problems over and over, and we somehow never really manage to solve it well enough that it is solved. So we're still doing routing and basic connectivity, whether it is IPv4, IPv6, NAT4.6, or the ability to translate between IPv4, IPv6. For example, we have really large-scale Cilium users running IPv6 only clusters, but nobody really manages to migrate to IPv6, so you still need the IPv4 connectivity. We can do this, as well as things like SRv6, service chaining for telcos. On the topology layer, so for the networking folks in here, we can do overlays, we can run BGP, and we can integrate natively with the cloud provider SDNs. So let's say you're running in an on-prem environment, you might be running a BGP control plane. If you're running on GKE, you want to utilize GC's networking layer and use Google's SDN layer. Same on Amazon and Azure, and so on. We also have a high-performance load balancing implementation, probably best known to replace kube-proxy, dominantly to replace the IP tables-based version of kube-proxy with an eBPF-based version that is more efficient. But we can actually do a lot more, maybe less known. We can also do load balancing into the cluster. You can essentially run Cilium on any Linux machine and turn that machine into a full-blown load balancer using the same load balancing technology as Facebook and Google are using. It's called maglev with direct server return. So you can get a bit of Google, a bit of Facebook, a bit of like hyperscaler load balancing technology in your own data center. Even if you don't need it, it can actually be fascinating. Latest edition, Kubernetes Ingress. Cilium now also comes with a Kubernetes Ingress controller directly integrated, so it takes care of all the layer 7 load balancing. Probably well known is that Ingress applies to the traffic into the cluster. Much well known is that you can also use it for east-west, for inside of the cluster, as well as for multi-cluster communication. So totally doable to use Ingress to define load balancing rules from one cluster to another. Network policy or network security. Obviously, we implement Kubernetes network policy. We do this a little bit differently than typically other CNIs do this. We are introducing the concept of a security identity. So instead of mapping and allowing IP addresses, similar to a service mesh, we are allocating security identities and allowing identities. In the latest version, we can even do this with MTLS. In prior version, the cryptographic aspect of this authentication was done using IPsec and WireGuard, the network level encryption. Obviously, we can extend that with Cilium network policy. These are network policy features that are not yet part of the Kubernetes network policy standard. These are things like layer 7 policies, DNS-based policies, service-based policy, as well as additional governance rules around network policies. Over time, many of them will probably find its way into the Kubernetes network policy standard. As I mentioned, obviously, we can also do transparent encryption for all the traffic on the wire. Then typically, at some point, you want to expand your network, your mesh, and actually go multi-cluster. Cilium has the ability to connect all of your clusters together without making clusters themselves aware of each other. You don't need to run federation or anything like that. You can essentially create one big network data plane. I would call it a universal data plane or similar, where from a networking perspective, all the pods can talk to each other. In the 1.13 version, we can now even connect clusters with overlapping pod or pod IP traffic as well. So you can actually use the same set of IP addresses for all your clusters. We can also run on non-Kubernetes machines or integrate external workloads. So it's possible to run Cilium, the agent, on a virtual machine or on a metal machine, for example, running a database, and integrate that entire machine as a workload into your Kubernetes cluster. That outside machine can then access the Kubernetes network, it can access kubedns, it can access the service layer, it can talk to service IPs, and you can apply network policy, and so on. That allows you to integrate external workloads without necessarily containerizing them. And the egress gateway, fantastic feature. Like your new world is in Kubernetes, your old world remains outside and is typically behind the traditional firewall. That traditional firewall is not cloud native aware, it is not container aware, it is still dumb, so it understands IP addresses, but your containers, your pods will constantly change IPs. How do you allow certain pods to talk through that firewall? Really hard. The egress gateway allows you to map container IPs, which are constantly changing, to static, stable IPs. For example, all pods in a namespace or all pods with a certain set of labels can be mapped to a set of IPs. You can then allow these IPs in your traditional firewall. So this is a neat and simple way to allow certain workloads in your Kubernetes environment through a traditional firewall. Switching topic to observability. I think initially we started Cilium thinking that the most of the advancement on the networking side is on the connectivity and on the security layer. We quickly learned that problem number one at day 2 with Kubernetes is actually on the observability side. What is going on? Who is talking to whom? How is my app doing? So we've created Hubble, which is using eBPF to extract observability data on the network and on the application level. So we can not only understand who is talking to whom, like from which pod is talking to which service and pod, we can even do things like HTTP processing entirely in eBPF, and for example, create a golden signal dashboard. A golden signal dashboard is a Grafana dashboard that will show you how well is my service doing, what is the latency, like how long does it take to query or use my service, did that change since I last deployed? Is the latency now worse? Is that correlated with CPU load? What is the rate of HTTP error codes currently served back to customers, and so on? It's the modern standard for application monitoring. You can do all of that at essentially no cost with Cilium. We also have Hubble UI. That's what you see on the right side. It's a global service map showing you all the services and how they are connected together. Again, on the network layer, all the way into layer 7 as well. So it understands every gRPC, every REST call. It understands Kafka, Memcached, and so on. So you not only understand what services are they doing or talking, you even understand which database table a certain service is accessing. All this observability data can be fed into a variety of open standards, open telemetry, of course, Prometheus metrics, and all of the logging can be fed into existing systems with FluentD. Cilium Service Mesh. Who is currently thinking about deploying or exploring a service mesh? Couple of hands. So I think service mesh is still relatively new. So let me actually talk a little bit about what a service mesh is, because it's not actually that new. That's usually the slide that's used when introducing what a service mesh does. So it does observability, security, traffic management, and resiliency when applications are talking. Like many of you will now say, well, we have been doing that before. We had observability before, we had security before, we had like traffic management. What is even traffic management? So let's connect some dots. And how did we do this in the past? Observability, of course, very low level TCP dump, NetFlow, SFlow on the networking level. Security, SSH, IPsec, VPNs, of course. Traffic management is essentially advanced load balancing. So we used to do this at layer 4. And resilience is essentially TCP retransmissions. So what is different with service mesh? The main difference is that we want to solve these problems at layer 7, at the application protocol level. So understanding protocols like HTTP, gRPC, and so on, instead of only at the network level. Initially, this problem was solved by embedding functionality that does this into the application itself. So companies like Twitter and LinkedIn or other companies that have been doing or running at web scale have been kind of introducing the concept or the function of service mesh by writing application libraries and doing so-called application instrumentation and linking this functionality, whether it's observability or mutual TLS or client-side load balancing using gRPC, into application libraries. This worked relatively well for the modern companies with a simple technology stack. If you talk to a typical enterprise, they're using every single application stack that's out there, and many of their applications are not even able to be modified. So you cannot link something in addition to it, which is why the concept of a service mesh sidecar proxy was introduced. So instead of changing individual applications, you're introducing an additional proxy component, and you embed the functionality, the HTTP processing, the load balancing, the observability into that proxy. This could be Envoy or Linkerd or HA proxy or Nginx. Doesn't really matter what proxy you use, you can embed this in there. Now you do this once and you can reuse this proxy regardless of what application framework is using this. You have decoupled the sidecar proxy, the functionality from the application. This was pretty neat, but has a lot of complexity that comes along with it, which was fine for like early days of web scale. It's definitely not applicable and not clean enough for wider adoption in the wider enterprise market, which is why the term service mesh has been coined. This is a little bit different for different type of customers, but we've seen complaints that up to 20–30% of the compute cost has been consumed by a sidecar proxy. And that's obviously not what you want. If you spend 20 or 30% of your cloud bill simply on like a sidecar service mesh proxy, that's probably too much. This essentially triggered the Cilium team, the Cilium community, to start thinking into Cilium Service Mesh. So we actually started a survey as part of the Cilium Service Mesh beta program, and this is kind of the summary of the feedback we've got. Cilium was already using Envoy for some of its layer 7 processing, but not in a sidecar configuration. So the feedback was very much, we love Envoy, but please find a way to get rid of this sidecar proxy architecture. This adds complexity and adds cost that we don't want. Maybe a little bit technical, but it's actually interesting. This is how a service mesh injects this so-called sidecar proxy, because the application does not want to be aware of this proxy. So you need to somehow inject it transparently. And some of you may have seen similar concepts way back using, for example, Squid or another proxy as an egress gateway for all the network traffic. Think about this in the same way. So it's actually using an IP tables rule on the network level to transparently redirect all the network traffic into a proxy, and this proxy then lives there and does all of the processing. So while this is transparent, it actually adds a lot of overhead from a networking perspective. Instead of having one connection between the applications, we now have a connection to the proxy, from the proxy to the proxy, and from the proxy to the app. So we went from one connection to 3 connections, and we're now traversing the Linux networking stack. That's millions of lines of code, 3 times instead of once. This is how it looks from a footprint perspective. Like we have a node with 6 pods. You would run one sidecar proxy, for example, using Envoy, 1 in each pod. That obviously adds quite a significant overhead. What we want to get to, and we're now no longer the only ones pursuing this model, is to essentially share this proxy. And that's not a fundamentally new model. Think about virtual machines and containers. Virtual machines had its own copy of the operating system and resources. The whole point about containers is to share the operating system, make it multi-tenant, use Linux namespaces to make the kernel and multi-tenant and share the resources and define rules on how the shared resources can be used, how much CPU can you use, how much memory, and so on. So the same concept reapplied to the proxy here would be what we are going for on the right. There are different models here. There could be 1 proxy per node, 1 proxy per namespace, 1 proxy per service account. Different use cases will probably benefit from different application topology models. What we are doing that is relatively unique, at least right now, is that we are splitting the functionality on how we implement service mesh between eBPF on the kernel level, that's where Cilium already operates, and Envoy. Which means that whenever we can, we actually remain in the kernel, for example, for HTTP visibility, for canary rollouts, for the MTLS. And then only if something is not possible in eBPF, we go to the Envoy proxy. And that gives a massive reduction of the footprint, a massive improvement of the network performance. So this is option 1. This is the new option that we have introduced earlier this year, where we are essentially providing a Cilium service mesh or a service mesh functionality entirely with eBPF and Envoy. Option number 2 is the option that has always existed. So that's the integration with Istio that Cilium had around the time, or since around the time when Istio went 1.0. That option obviously continues to exist. So if you want to run a sidecar-based model, you can continue to do so. From a Cilium service mesh perspective, we actually truly believe in that we are a really good team, or Cilium is a really good opportunity to provide the best possible data path. We're kernel developers, so we don't try and recreate the control plane because we will be relatively bad at that. So we will look at supporting existing control plane options, and we currently see Gateway API as the likely standard that will be dominant and will be a good mix of powerful or power versus complexity for the majority of users, as well as SPIFFE as the so-called identity management provider. So this is the solution that provides the security keys, the certificates, the service-specific certificates, or the SSL certificates that will be used for the mutual authentication between the services. As I mentioned, we're now no longer the only ones pursuing this model. We've been talking about this model for a while. In fact, I even found a slide around this in the first ever Cilium presentation we've done. It was a big topic at Service Mesh Con in Europe a couple of months back. Recently, the Istio project has announced Ambient Mesh. It's a subversion of Istio. Istio used to be entirely about sidecar proxies. Ambient Mesh is now a subversion of Istio that now also supports a sidecar-free data path option. So we will probably see across the service mesh space that there will be a sidecar-free and a sidecar-free option for the majority of service meshes. In the end, if I would paint the vision, this is really how I see service mesh evolve. On the left is what we started out with, which is service mesh functionality is embedded into the applications themselves, right? So Python as part of a Python library or a Go library and so on. The intermediate step was, let's use a sidecar proxy. And I think the future is really to see this as part of the operating system. Just like TCP simply exists right now, service mesh is really a modern incarnation of values that have typically provided by the operating system. Once it's part of the operating system, it's completely transparent and it's standardized, and I think that should be the ambition of service mesh functionality as well. That does not necessarily mean that all the functionality needs to run in kernel mode. So speaking as a former kernel developer, a lot of you using Linux out there, the kernel actually utilizes the user space mode a lot. For example, when you connect to a Wi-Fi network, a lot of the complex negotiation logic is actually running in user space. Or when you plug in a USB device and the Linux kernel automatically loads your USB device driver, it does so using a kernel mode or user space helper to load the kernel module. It's simply an implementation detail. And this will be very similar here for service mesh, that a combination of eBPF and Envoy together will implement the data path portion of service mesh. And we will see service mesh as a next generation, as a modern layer of network functionality. In terms of multi-tenancy, I think this will remain fluid. Whether we run sidecars, one per pod, one per node, or even a share proxy on the network, that has pros and cons in terms of increased performance, increased efficiency, and decreased isolation. However, increased isolation is not always good. It also means that we lose some aspects around resource management. Think about Kubernetes. If you're running 20 pods on a node, you can actually utilize the available CPU resources much better in a best effort manner instead of running 10 VMs and give guaranteed resources to each VM. So this is always a trade-off, and similar to how there is never an ideal scenario to only run containers or only run virtual machines, it will be very similar in this instance as well. Let's switch gear and talk about Tetragon. This is the last aspect of Cilium. Tetragon is a new open source project that we have released earlier this year. It is runtime security and observability. And that has existed before. Who knows about Falco or Tracy? Excellent. So Tetragon is very similar. Falco actually also uses or also has an eBPF probe or an eBPF mode. Tetragon is only eBPF. There's one fundamental difference. It is that a lot more additional logic is in this kernel space, and we'll talk about what that difference is. Tetragon can do both. It can give you security-relevant observability across the stack, so from very low levels, like who is accessing certain devices, who is doing certain network calls, namespace, escapes, privilege escalation. So for example, who is breaking out of a container namespace, so the typical container escape, as well as processes escalating privileges. So this could be, for example, a Kubernetes pod getting scheduled with additional capabilities, such as network administration privileges or root or other, for example, raw socket access and so on. File access, who is accessing which files. Network layer, for example, to observe TCP sequential number attacks, all the way into the process, like who is launching which process, who is forking, system call activity, who is accessing certain files and so on, like all of the system call activity, all the way into even understanding application function calls to do function tracing. So Tetragon has this massive layer of observability, and we'll see a couple of examples. Based on this observability, we can also do enforcement. And I won't talk too much about that because we'll have a slide on that. I will make it clear like what is new about Tetragon. And this new aspect is actually very crucial and important. So when we talk about runtime security, it is always about detecting malicious activity in real time. What that means is that in practice, or also in theory, not only in practice, it is strictly better to detect malicious behavior in real time and prevent it, instead of reporting to a system and analyze it later on. I mean, analyze it later on is better than doing nothing, but preventive security is best. So that's what we focus on primarily. We're not the first ones to do this. Some of you may remember early security solutions using LD preload. Who knows what LD preload is? It's a pretty old Unix, excellent old Unix concept. So it's an environment variable that allows us to essentially link an additional shared library to an application without telling the application. The application can actually detect this, so it can notice when a shared library gets attached. This is frequently used to essentially link or add an additional layer, and this layer acts as the replacement, as a wrapper, as a shim layer to all system calls being made. This has been the early versions of doing system call security. Definitely not the way to go, because simply statically linking prevents or circumvents this security layer altogether. So it's very basic and obviously no longer used in practice. Obviously, we can do system call filtering in the kernel itself, and this has been done over and over again. You probably heard about ptrace early on, seccomp, and even eBPF kprobes on C system call entry. This is functionality built into the kernel directly. These attempts or these architectures are all vulnerable to this time of check, time of use type attacks, which means that the time the parameters of the system calls are being checked is before the last point in time when the application can still change the attributes, which renders obviously the whole system useless. So I can go in and say, I want to open this file, the system checks it, says, okay, great, you can go ahead, and then the application can still change the file that it actually accesses. So also of very, very limited use, which is why latest technologies such as LSM or SE Linux are deeper down into the kernel level that prevent or avoid this type of attack. There is even an eBPF mode of LSM. It's called eBPF LSM, so it's the ability to use the Linux security subsystem, the LSM API, and use eBPF. Tetragon, the downside of this is that this needs very, very, very new kernel versions, 5.7. This is very recent. Tetragon essentially goes beyond this and does not depend on LSM, but has all the benefits of LSM. I know this was quite technical, but essentially it's an evolution of a set of security solutions that existed before, and Tetragon goes along and increments or uses the benefits of it, but can also work on older kernel versions. So even if you're on an older, for example, a Red Hat Enterprise Linux kernel, you can still use and utilize Tetragon. The benefits of this is that we gain all of this observability with this, all of this very deep observability, all of the transparency and all of the low overhead, and can run that on any kernel version with any application that we want. So there is no application-specific concept. We don't need to change the application. We can essentially gain observability on any Linux system with a kernel newer than 4.9, which is it's also not super old, but even a RHEL 7 will be able to fulfill the requirements. Examples on what you can extract, for example, SSL visibility. Maybe you want to know what are the ciphers that are used by my applications. Is any of my applications using a cipher that is insecure? Or the cipher key length may be too short? Or is a malicious attacker attempting an SSL downgrade or a TLS downgrade attack, so maliciously trying to negotiate an insecure or less secure cipher version? Or even just extracting the SNI names. This is actually great to understand what are the remote destinations my applications are reaching out to. We can then go in and, for example, feed this into Splunk and query it early on and say, let me know which applications are using TLS 1.1 or 1.0, like older insecure versions of TLS, or what applications are using older or insecure versions of particular ciphers. We can go further and say, let me look at entire network traffic, and not just on the network level, but actually understand the DNS resolution, the network layer, HTTP, the connect system calls. You actually see this is an example of curl being invoked against Cilium.io, and you can see every single system call as well as every network activity. You can even see the Kubernetes DNS resolution attempts where it tries to resolve it as an internal service name, and then finally, eventually, it resolves just pure Cilium.io and gets an IP returned. Even all the way to even understanding the actual number of bytes and number of packets that have been associated with the connection. Very interesting, you even see that because we have been accessing Cilium.io on port 80, you see how the website actually redirects using HTTP 301 to the secure SSL version of the website. So very interesting to explore even basic use cases like this and understand what the system actually does. Other ideas here, detect DNS bypass attempts. A Kubernetes pod that instead of talking to the Kubernetes DNS pod, just tries to talk to a different DNS server directly, potentially resolving to the incorrect IP. Gets even more interesting as we start to combine the network visibility with the runtime visibility. Typically, these have been decoupled. We had system call visibility tools, like what are the system calls that are happening, and we had network observability. If we can combine the two, we can visualize this nicely, and in this case, we're actually seeing a Kubernetes worker node with kubelet, with kubeproxy, and we see which individual process, who has started these processes, and what type of network connections they open. If we go into enforcement has typically been done this way. This is how, for example, Falco works, but also other solutions as well. They have a so-called kernel probe, and this kernel probe extracts visibility, similar to what we have seen before. For example, what system calls are being made, what network connections are being made, and then this kernel probe sends this observability data to user space, and in user space you have a big filter engine, and this filter engine is looking for patterns that are potentially malicious, and if it detects a malicious pattern, it will then kill the process asynchronously, right? But the process was allowed to continue to run while these notifications, while this observability was sent to user space, then the filter engine in user space needs to process that, and then the connection or the process gets killed afterward. That's still better than not doing anything about that, but we're actually not preventing, we're only reacting. If we're talking about enforcement with Tetragon, all of this filter engine, this logic, is moved into the kernel, which means we can actually, as it happens, detect and then react immediately in real time, which means we can prevent the majority of attacks as they happen, instead of sending asynchronously all the user space up, all the notifications to user space. And this is a big change. It's not the first time this type of change happens. We've done this before on the observability side with eBPF. Some of you may have used perf, the performance troubleshooting tool on Linux, has the same concept. Instead of sending a lot of raw observability to user space, it uses eBPF in the kernel to create histograms and metrics and so on. And this has unlocked a completely new level of doing observability. Some of you may have heard about Brendan Gregg. He's done great talks about flame graphs, how to do performance troubleshooting. This is the same concept, but applied to runtime enforcement and runtime security. And we'll see a big wave. We will not be the only company exploring this. There are already several other security vendors pursuing this as well. This will be the new standard on how to do runtime enforcement on Linux. This allows us to do, for example, this. This is a Tetragon YAML file here saying if anybody writes to the authorized keys or to the shadow file, immediately kill the process. And we see an example. There is a pod here accessing the shadow file, and as it writes to it, the process gets immediately killed. It will not manage to actually write to the file. It will get killed before it can write to the file. Or we can detect remounting of root, other typical attack that's done with containers. Or even, and this gets even better, if a process, for example, manages to escalate its privileges. So, for example, container gets compromised and it gains capsys admin capabilities. That's essentially the equivalent of root. Then it could, in theory, write and read every file. With Tetragon, we can still prevent access to certain files, despite this container, this pod, this process with escalated privilege. That's the benefit, that's the power of eBPF that allows us to do these new things. And again, in real time, so instead of just reactively killing the process after the incident has happened, we can actually prevent the attack. And with that, I think we have a couple of minutes left for questions. In the meantime, as you prepare your questions, if you're interested to learn more about Cilium and eBPF, obviously Cilium.io gives you the insights and the starting point to the Cilium project, whether as a user, as a customer, as a developer. eBPF is the community page around eBPF if you want to learn more about the magic of the underlying kernel layers. Very exciting and I would say also very interesting. In particular, there are lots of really nice eBPF Summit recordings, like conference recordings. from like eBPF co-maintainers to how Facebook uses eBPF, all the way into how financials use Cilium and so on, so the whole spectrum. And if you're interested to use Cilium in a commercial and enterprise setting, feel free to reach out to us at Isovalent.